Yeah, thanks a lot for the invitation. So I'm going to talk about control issues of KKLT today. And this talk is based on a recent paper with Xingao and Arthur Ebiker. So let me start with a brief outline of this talk. At first, I will give a short introduction where I will review some key aspects of the KKLT scenario, which will be relevant for this talk. Then I will discuss what we call the singular bulk problem. If time permits, I will also say a few words about possible escape routes to this problem. And finally, I will conclude with some remarks about possible future research. Okay, so as you all know, a long debated question in the literature is whether de Sitter vacua are possible in string theory. On the one hand, there are several plausible and popular scenarios for such de Sitter constructions, for example, the KKLT scenario or also the large volume scenario. But one should also say that at this point, these scenarios are not fully explicit yet. On the other hand, it's well known that there are many no-go theorems which constrain either the existence or the stability of de Sitter space in various corners of string theory. So here I've displayed two classic references for such no-go theorems, but there are many more which apply to various situations. So one might wonder whether there could be something like a no de Sitter conspiracy in string theory. And in recent years, this general idea has been made more explicit in terms of, for example, the de Sitter conjecture or the refined de Sitter conjecture. Yeah, so could something like this possibly be true? Well, I think it's fair to say that at this point, we don't really know for sure. And for this reason, I think it's crucial to keep trying to construct explicit models which realize these de Sitter scenarios. But on the other hand, we should also be open to the possibility that there are some problems hiding in the details of these constructions. And then we should try to identify these problems. And this is precisely what I would like to do today. And in particular, I want to focus on the earliest and presumably most studied proposal for such a de Sitter construction, which is the KKLT scenario. So let me quickly review some aspects of this proposal. The idea is to construct metastable de Sitter vacua in 3 steps. The first step is to consider type 2b, or more generally F theory, flux vacua, which have a strongly warped throat region, which is locally modeled by the Klebanov-Strassler solution. So this is what I've tried to draw here in this cartoon. So this is supposed to be the throat region. And this throat is characterized by flux numbers k and m, which carry a d3 charge, k times m. And in this talk, I will just denote this by n. So here we have some d3 charge sitting, which is localized in the tip region. The second step is to stabilize the Kähler modulus T using some non-perturbative effects. This could, for example, be a Euclidean D3 brane instanton or also a Gaugino condensate on a stack of NC D7 branes. And one can argue that this then leads to supersymmetric ADS vacua with the following vacuum energy density. So V ADS goes like e to the minus RET over NC. And here I'm ignoring any non-exponential prefactors in front of this exponential function here because they won't play a role for the argument. And let me also ignore order 1 numerical factors in front of this RET term here in the exponent. If you're interested in these numerical factors, you can look them up in our paper, but they won't play a role in the following. And let me in the following furthermore set NC equals to 1 just for simplicity, and I will comment on the more general situation where NC does not equal 1 later. Okay, the final step is then to uplift this ADS vacuum to de Sitter by putting an anti-D3 brane into the throat region. And one can argue that the energy density of this anti-D3 brane is then redshifted due to the strong warping. And this then leads to an uplift contribution to the vacuum energy density, which goes like this. So e to the minus k over GSM, where k and m are again these flux numbers that I just introduced. And one then finds that this leads to metastable de Sitter vacuum if the uplift energy is not too large. So essentially what you have to demand is that this uplift contribution is of the same order as the ADS contribution. So here on the right-hand side, I've drawn the scalar potential and its dependence on the real part of the Kähler modulus. Here you can see the potential excluding the uplift term, so just the potential that leads to the ADS minimum here. And this is the uplift term. And essentially the condition is that this here is roughly of the same order as this magnitude here. If the uplift term is too large, then you will just get a runaway. And if it's too small, then the sum of these two terms here will lead to a minimum, but it will be an ADS minimum. So roughly these two contributions have to be of the same order. And yeah, if I just plug in what I wrote down here and on the last slide, then I get this condition here. And then I can set equal these exponents and use that n equals k times m by definition. And then I find this condition here for the real part of the Kähler modulus. So a successful de Sitter uplift requires RET to be of the order n over GSM squared. Okay, so another thing that I will be using in the following is that this factor GSM squared in the denominator here is actually a large parameter. And why is that? Well, for one thing, we know that GSM has to be order 1 or bigger in order for the curvature at the tip of the throat to be small. And we also know that M has to be roughly bigger than 12 for the metastability of the anti-brane. So GSM squared is roughly 12 or bigger, so it's a large number. More recently, there was also a series of papers which argued for an even stronger bound on GSM squared, namely 6.8 squared, which is roughly 46. And this bound is based on an instability of the conifold modulus, which needs to be prevented. For us, it's not going to be important what the precise numerical value is, but I will treat GSM squared as a large parameter. Okay, yeah, an interesting observation was made in this paper here by Carter et al., where the authors found that precisely in this regime where GSM squared becomes large, it seems that the strongly warped throat is so large that it actually does not fit into the weakly warped Calabi-Yau bulk anymore. And the authors also worried that this might lead to large singularities. On the other hand, it's not fully clear whether this is really a problem, because what this tells us is just that the assumption that we can separate the compact space into a strongly warped throat region and the weakly warped bulk region, this assumption just breaks down in this regime. So in other words, we have a strongly warped compactification where the warp factor cannot be approximated as a constant anymore. It's a varying function. But a priori, this does not mean that there's anything wrong with the supergravity approximation. In particular, even the varying function can, of course, still be positive everywhere, and the volume could in principle be large everywhere, and the curvature small. So a priori, it's not fully clear whether this is really a problem. So what we need to do in order to find out is we need to study the warp geometry in more detail in this regime where GSM squared is large. And this is what I'm going to do in the next part of my talk. Okay, so let me discuss in somewhat more detail what we call the singular bulk problem. So let me consider a type 2b on some conformally Calabi-Yau orientifold with the following metric. This is the 10-dimensional metric here. This is the 4-dimensional external spacetime part with some warp factor, which I call h of y, and y are the internal coordinates. And I also have some internal 6-dimensional part, which is given by some conformal factor times a Ritchie flat metric, which I denote by tilde g. And let me normalize this tilde g factor such that the volume as measured with this tilde metric equals 1. And further recall that the Kähler modulus T is defined in terms of the Einstein frame 4-cycle volume, which is wrapped by the E3 instanton. I will just denote this 4-cycle by sigma in the following. So essentially what we have is that the real part of the Kähler modulus is given by the dBi action of this instanton. And as I told you on the last slide, this has to be stabilized at n over GSM squared. So when I just plug in this metric here into this expression, then I get this relation here. So the integral of the warp factor over this 4-cycle sigma has to be of the order n over GSM squared. I'm also going to use that the 6D Calabi-Yau volume can be expressed in terms of the 4-cycle volume using triple intersection numbers. And this is then what I get here. So this is the volume of this 4-cycle sigma in tilde g. It's given by this expression here. And since the triple intersection number is an integer and I've normalized tilde v to 1, I find that this 4-cycle volume is order 1 in our normalization when I measure it with this tilde metric. All right, now I can use this relation and divide it by this relation here to get an expression for the averaged warp factor over this 4-cycle sigma. So what I get is that the average of the warp factor on sigma is n over m squared. And this is here my definition of the average. I just integrate h over sigma and divide by the volume in tilde g. Okay, yeah, so we've found this expression here for the average. And of course, the average can only be n over m squared if there is anywhere on sigma some neighborhood where the actual value of h is also n over m squared or smaller. So I find that there must be a neighborhood on sigma where h satisfies this inequality here. On the other hand, I also know from the equations of motion that the warp factor satisfies a Poisson equation, namely this one here. So tilde nabla squared, that's just a Laplacian on our Calabi-Yau manifold with respect to tilde g. And here on the right-hand side, I have some D3 charge density tilde rho, which includes anything that is charged under the corresponding Raman-Raman field. So anything that carries D3 charge, this could be actual D3 branes or O3 planes or 7 branes, which have D3 charge. Could also be 3-form fluxes. They also carry D3 brane charge. So anything that carries such a charge contributes here to this charge density. And now recall that I told you in the beginning that there's this D3 charge N dissolved in fluxes, which sits at the tip of the Klebanov-Stressler throat. And this D3 charge actually sources the warp factor. And when I then go an order 1 distance away from this source, then this has the effect that the warp factor varies at the order GSN. Why GSN? Well, I have this coupling factor GS here in the Poisson equation and my charge is N. So the variation of the warp factor will be of the order GSN. Okay, so now I can use this relation here and divide by this relation, and then I get the following inequality here. So I find a neighborhood on this 4-cycle sigma where the variation of h divided by h itself is actually a large number. So H varies quite strongly in this neighborhood. And yeah, now I can use this information to infer the existence of a singularity. In particular, what I can do is I can just pick some point, why not, on this neighborhood and then do a Taylor expansion, as I've done here. And then I can use this inequality that I just derived in this expression here. And what this tells me is that this first order Taylor coefficient essentially equals the zero order Taylor coefficient times GSM squared. So I only need to go a parametrically small distance delta y away from my initial point until these two guys here become equal. And then what I find is that H goes through zero and becomes negative. So at a parametrically small distance from this point that I chose in this neighborhood, I find a singularity. Now, here I should say that H is not an arbitrary function. Actually, as I told you on the last slide, it's determined by this Poisson equation. So I expect that H equals GSN times an order 1 function, which itself does not depend on any small or large parameters anymore. So I expect generically that all Taylor coefficients are of the order GSN, and then I'm also allowed to do this Taylor expansion here and truncate at least 4 parametrically small distances delta y. So this argument should go through. There's one exception, namely when I happen to pick a point y naught where this first order coefficient is 0, so when I'm at an extremum. But then actually I can repeat almost the same argument using the second order Taylor coefficient. I'm not going to do this here, but it's in the paper if you're interested. In any case, one infers that in this neighborhood or very close by, there must be such a singular region appearing. Okay, before I continue, let me just summarize what I've told you so far. I've told you that step 1 of the KKLT proposal requires a flux compactification where the volume modulus has to be stabilized at n over GSM squared. And we also require a conifold region with a D3 charge n. And I've then argued that this value of RET is actually too small to ensure that the curvature is small everywhere. Instead, what happens is that this large D3 charge n leads to a large variation of the warp factor, and this then creates singularities in the bulk. Okay, let me also say a few words about how large this singular region is actually. Well, I've just told you that the variation of H is much larger than its average in this region on sigma. So this is what I've tried to draw here. So these are the directions parallel to this 4-cycle sigma. And as you can see here, the average is quite small. It's n over m squared. But then the variation of the warp factor along sigma is rather large. So it varies of the order GSN over an order 1 distance. And yeah, now it's obvious that this negative region and this positive region here, they roughly have to be of the same size in order to be able to almost cancel out in the average and produce this small average here. So we can conclude that the negative region of the warp factor must be an order 1 fraction of the C3 volume as measured in the tilde metric. And yeah, generically, this then means that the singularity also spreads over an order 1 distance into the transverse space. So by generic here, I mean that the warp factor does not vary parametrically stronger along the transverse directions than it does along the sigma directions. So in other words, the singularity is not unnaturally thin. And if that holds, then I can conclude that actually an order 1 fraction of my original Calabi-Yau is covered with this singular region. So clearly we have discovered that our original assumption that we started with, namely that we have the supergravity approximation is trustworthy, that actually seems to break down in a large part of our compactification space. There's also a complementary argument coming to the same conclusion, which involves discussing a coarse-grained warp factor. I don't have time to discuss this now, but if you're interested, you can look it up in our paper. Okay, I think I still have a few minutes left to discuss some possible escape routes to this problem. So one thing one should say, of course, that our argument is based on genericity. So we make parametric estimates of how strongly the warp factor should vary in the bulk, but there might be specific models, special geometries, which for one reason or the other avoid these generic parametric estimates. So I've drawn one particular example here that came to our mind. What one might imagine is, for example, that the charge that sits in the throat region is screened if the O-planes have a very special arrangement here. So when they sit all in this, at the end of this throat region, then the bulk won't see any monopole charge anymore. And then I won't expect that the warp factor has a strong variation. So in that case, one might be able to evade our singular bulk problem. I don't know if such a model can exist, but it's certainly very ungeneric, but I don't know if this is possible. So it's certainly an interesting question for model building to find such geometries. Another thing is that large NC seems to help. Recall that I initially set this factor NC equals to 1, but when I just decide to keep it and repeat my argument, then what I find is that this inequality that I just derived receives this additional factor NC here in the denominator. So this large number GSM squared, which caused all the trouble, could in principle be canceled by making NC large enough. However, this idea actually does not work, at least for a single Kähler modulus, because it was found in this paper here that NC is actually bounded. In particular, for H11 equals 1, it's bounded by some order 10 number. So you can, at best, alleviate this problem, but you cannot parametrically avoid it. Yeah, so one is naturally led to generalizations and variants of KKLT where the number of Kähler moduli does not equal 1. And I'm not going to go into the details here, but we actually studied quite a lot of such models. And in the end, we all found that all of these ideas still suffered from a singular bulk problem, and we weren't able to parametrically avoid the problem, even in this more general situation with several Kähler moduli. There's one possible exception that we could not parametrically rule out. It's quite contrived, but again, we cannot rule it out. So let me just state it here. Turns out that if you consider a model where H11 is parametrically large, and at the same time you have a large number of large D7 stacks, such that the total D7 tadpole is of the order H11 squared, then we could not find a parametric argument anymore. So it is possible that such models, if they exist, avoid our problem. But let me emphasize here that this is only possible if you have a huge D7 tadpole, H11 squared. I'm not aware of any model which has this, but I cannot rule it out, so it would be interesting to look for such models, or perhaps try to find a no-go theorem that excludes such large D7 tadpoles. All right, yeah, let me conclude. I have told you that flux compactifications admitting a KKLT like de Sitter uplift generically have large singularities, which extend over an order 1 fraction of the original Calabi-Yau manifold. And these singularities arise because there is a large charge n sitting in the KS throat, and this charge leads to a too large variation of the warp factor in the bulk. And when you combine this with the fact that you have to fix the warp factor at a specific location in the bulk to a rather small value, then this large variation has the effect of large singularities, which indicates a control problem of my compactification. I've briefly discussed a few possible ways to escape these conclusions. So it would certainly be interesting to look more into this and perhaps find specific geometries which avoid our estimates, or find models with a very large D7 tadpole, or else find no-go theorems which exclude these possibilities. So that's certainly something that one should investigate in the future. And yeah, finally, I've very briefly mentioned the large volume scenario at the beginning of my talk. The large volume scenario appears to avoid the singular bulk problem. This is essentially because in the large volume scenario, the volume is exponentially large. So one would not expect strong warping effects there. The warp factor is essentially constant, and then this problem does not appear, at least to our current understanding. On the other hand, if one takes conjectures such as the de Sitter conjecture seriously, one might wonder whether there could still be some other hidden problems in this scenario. Although I don't have a specific suspicion at this point, it would certainly be important to investigate this further and yeah, perhaps see if there's something hidden in these constructions that prevent the creation of explicit models. All right, that's all I wanted to say. So thanks a lot for your attention.
Okay, thanks very much, Daniel, for the very nice talk. Let's all thank Daniel with our clap emojis. Are there any questions? Well, while we're waiting for other questions to come in, can I ask, so in F theory, it's often very easy to find these very large tadpoles, but of course you run into the problem of finding order 1 G string in many regions of the compact space. Do you have any comments on how these two things might play together?
So you were asking about large tadpoles, and what was the other one? Large G string?
Oh, just, well, you have the trade-off between many D7 or more general 7-brain stacks in F theory. But you have to, and large tadpoles, but you have to trade that with finding order 1 G string inside your compactification. So it seems like that helps in one way, but doesn't help in the other, because now you have to worry about strong string coupling.
Well, I wouldn't say that large tadpoles necessarily help. At least they didn't seem to help in the models we considered. You are talking probably about these models with several Kähler moduli that we looked at, because
yeah, that's right,
the tadpole actually played a role. For the initial argument, the precise number of the tadpole didn't even play a role. But if you try to avoid our argument and go to models with several Kähler moduli, then one can actually play a game in trying to increase the Kähler moduli in a certain way, try to avoid this problem, but then you actually need tadpoles which are ridiculously large, and like even much larger than the largest known tadpole in F theory, which I think is something like 7.5 times 10 to the 4 or so. So even in this model with the largest known tadpole, you cannot avoid the problem. You would need 1 or 2 magnitudes, order of magnitudes higher.
I see. Okay, thanks. Mankey has a comment.
Yeah, I think one of the possible escape route that you mentioned, that the screening is not such a crazy thing to happen. What we've seen in cases where we generate the conifold by collapsing some curve in the mirror dual is that the conifold is at the place where is obtained by intersecting prime toric divisors. And when you make the 7 planes by like taking orientifold that flips the signs of some homogeneous coordinates, those 7 planes typically are at the prime torics, and those prime torics also intersect, goes quite close to the conifold point, so that you can imagine a picture where conifold is wrapped by some kind of 7 planes in the UV, and then if you place the 7 brains on them, then you can effectively screen the charges.
That would be very interesting if you can make that work. I mean, it's. I don't know how much you have looked into this, but it's certainly also non-trivial to check then where the instanton sits or where the non-perturbative effect on the D7 brane sits. I mean, you would basically have to place that behind all the stuff that screens the charge. Otherwise, it doesn't help much. So, I mean, if you have a concrete model where this seems to work out, then this is very interesting. So, be interested in hearing more about this. But a priori, it doesn't seem to be trivial for me that one can do this.
It's not certainly generic, but it is not so hard to find such a model.
Okay, maybe you can tell me some more details about this model you had in mind. That sounds interesting.
Okay, our next question is from David.
Hi, yeah, thanks a lot for the nice talk. So I just wanted to understand the last thing you said on your last slide. So you said indeed the singularities arise because there's this large charge which leads to the large variation. But you also mentioned that the problem was that the warp factor was fixed at a small value, and it was the combination of both which was problematic. And I just wanted to be sure to understand what fixes it at a small value actually.
So the problem is that because of moduli stabilization, I have this condition on the warp factor. Initially, I told you that in order to have a successful uplift, I need to stabilize the Kähler modulus at this value here. And then I went through a few steps. Then I arrived at this relation here for the averaged warp factor on this instanton cycle. So this tells me that the variation of the warp factor in this region is parametrically larger than the actual size of the warp factor in this region. If I were allowed to make the volume modulus as large as I want, then I could always avoid this problem. I can just go to the limit of infinitely large volume, and then the variation of the warp factor will become negligible at some point. So then I enter this usual large volume regime where the warping is approximately negligible. But here I have to stabilize the volume modulus at a relatively small, still large in string units, but relatively small value compared to the variation that I expect. And that's the issue.
Do I view this correctly, that in your graph of the warp factor, this amounts to shift the vertical average basically, while leaving
the volume modulus in warp compactifications is a shift of the warp factor.
Very good. Yeah, thanks a lot.
All right, if there are no other questions, let's thank Daniel one more time.